So, um, if a submarine hull breaches, heavy watertight doors slam shut to seal off sections and, save the ship, well, right now, you are likely sitting in a building engineered to do the exact same thing.
Right, but instead of holding back water, it is holding back superheated gas and, well, fire?
Exactly. And that is our mission for this deep dive. We are decoding the hidden life-saving architecture
Yeah.
secretly built into the walls around you.
So, okay, let's unpack this because I think people really misunderstand how this actually
Oh,
works.
they definitely do. The key shift here is moving away from the whole idea of fireproofing. Because, nothing is permanently fireproof.
Right, given enough heat, like everything burns or melts eventually.
Yeah, exactly. Instead, the industry relies on really rigorous testing metrics,
Hmm.
like the ASTM E119 time temperature curve. We are talking about materials tested against a fire that hits over 1,000 degrees Fahrenheit in just 5 minutes.
Oh, wow, in just 5 minutes. Yeah, and then nearly 2,000 degrees after a couple of hours. So the engineering here isn't magic. It's strictly about buying a specific amount of time for evacuation and, firefighter response.
Right, buying time. And to understand exactly how a building buys you those precious hours, we kind of have to look at the physical barriers down to the chemistry. Like, take a standard fire-rated wall using Type X gypsum board.
Right, because it's not just a thick piece of rock.
No, not at all. The critical mechanism is actually calcination because about 21% of gypsum's weight is actually chemically bound water. When it gets hit with that extreme temperature curve, that water turns to steam.
Right, so it actively absorbs thermal energy.
Yes, essentially cooling the unexposed side of the wall while the fire side is just, burning away.
Which is just this brilliant endothermic reaction baked right into the architecture. But an assembly is really only as strong as its weakest point. I mean, you can have a 2-hour calcining wall barrier, but if you have a standard window in that wall, you introduce thermal shock.
Wait, really? So standard glass is essentially a giant weak spot in the building's chainmail.
Completely. Because standard glass heats unevenly. The center of the pane expands rapidly from the heat, but the edges stay relatively cool since they are hidden inside the frame.
Oh, I see. So the stress just causes it to shatter.
Right, that mechanical stress causes the pane to shatter in minutes. It gives the fire a massive free pass to spread, which is exactly why fire-rated windows are the unsung heroes of the system.
Matching the thermal resistance of the walls. And that modern fire-rated glass, it isn't just thicker glass to resist that shock, right? The sources say it uses intumescent layers.
Exactly. Between the panes of glass are transparent intumescent interlayers. So under extreme heat, the outer pane might still shatter, but that inner layer chemically reacts and expands into a thick, opaque, solid foam.
That is wild, just turning into foam?
It really is. And that foam doesn't just block the physical flames, it blocks radiant heat. Because in a commercial hallway fire, radiant heat alone can be intense enough to spontaneously ignite materials on the other side of the glass, or, severely burn evacuees running past.
Wow.
Mm,
Okay, so we have calcining walls and intumescent windows creating these highly engineered safe zones, guarding commercial stairwells, elevators, or sensitive zones in hospitals.
hmm.
But here is where it gets really interesting. Because having this invisible armor doesn't matter if it's messed with, right?
Oh, absolutely not. Which
Yeah.
is why, local code compliance and documentation are so strict.
Yeah, because say I try to DIY a modification, like shaving 1/8 of an inch off the bottom of a fire door just to clear a new carpet. Do I instantly compromise the building's safety rating?
You do. If we connect this to the bigger picture, it really comes down to the physics of positive pressure.
Right, the fire pushing the air around.
Yes, a real fire creates immense atmospheric pressure, pushing smoke and superheated toxic gases through the tiniest crevices. Fire doors rely on their own intumescent seals hidden in the frame that expand to fill very specific, factory-designed gaps.
Ah, so if you arbitrarily increase a gap by 1/8 of an inch, the seal just cannot bridge that distance.
Exactly. Superheated gas blows right through the perimeter of the door. You completely compromise the stairwell you are trying to use to escape.
That makes you look at facility management in a totally different light. These materials, the steel, concrete, and even the new eco-friendly ones the industry is exploring, they can last for years, but only if they are perfectly maintained.
They do. But physical safety isn't just the hardware. The intumescent seals, the calcium gypsum, they only function if the software is running correctly.
And by software, you mean the people inside.
Exactly. Staff training and regular fire drills, the doors actually have to be closed. If hospital staff prop open a heavy fire door with a wedge for convenience, the millions of dollars spent engineering those thermal barriers is completely useless.
right? Human behavior has to align with the engineering. So the next time you walk through heavy double doors in a hospital, or you take a trip down a commercial stairwell, take a second to look around. You aren't just walking through a hallway, you are stepping through a highly engineered, heat-tested safe zone.
Yeah, you are navigating a space designed with a very specific ticking clock in mind, which leaves an unsettling question for you to consider. Since these submarine-like systems are explicitly rated to withstand that 2,000-degree curve for a set number of hours, what exactly happens to the structural integrity of those spaces the very second that clock runs out?